Today we will talk about the MPLS overview and static LSP implementation. And our focus is on three parts: basic MPLS concepts, process of forwarding labeled packets, as well as related implementation on Huawei products, basic configuration of a static LSP. First, let's look at the overview of MPLS. Before introducing MPLS, we need to review IP routing concepts. To put it simply, when a Layer 3 device receives an IP packet, it searches its routing table for the destination IP address of the packet. If a match is found, the device forwards the packet over the matching route entry, which contains an outbound interface and a next hop IP address. If no match is found, the device discards the packet. There are two issues with IP routing in the early phase. The first one is that IP routing was implemented using software, which was time-consuming. And the other one is that devices had to process route recursion. IP routing was slow in the early phase due to various reasons. Many solutions were proposed in the industry, including asynchronous transfer mode, ATM, and MPLS. MPLS gradually dominated in the architecture and applications on IP networks. To put it simply, MPLS adds a label header to an IP packet. The label header is placed between the Layer 2 frame header and Layer 3 IP header. When a labeled packet is forwarded on an MPLS network, devices merely need to check the label value in the label header. Let's go through the background of MPLS and IP routing, as well as the problems in IP routing in the early phase. With the development of application-specific integrated circuit, ASIC, and the emergence of fast forwarding technologies, the route searching speed was no longer a bottleneck of network development. MPLS supports multiple labels and a connection-oriented forwarding plane, which makes MPLS widely used in VPN, traffic engineering, TE, and quality of service (QoS) applications. What is MPLS? At the data plane, MPLS adds a label stack containing one or multiple labels between the Layer 2 frame header and Layer 3 IP header, and forwards the packets based on labels through an MPLS domain. MPLS is an IP backbone network technology that supports multiple upper layer protocols. Therefore, MPLS supports various service types. In typical MPLS applications, MPLS VPN is widely used. In this example, an MPLS VPN backbone network is constructed by a carrier and provides VPN services for customers. The routes and data of different customers can be transmitted through the public network without mutual interference. Routes and data of different customers are completely isolated, even if they are carried over the same carrier network. MPLS applies to both carrier and enterprise networks. One of the most common scenarios is the MPLS application on the e-government Extranet. MPLS runs on the public network constructed by the government. On such a network, multiple types of services are transmitted and logically isolated. Next, let's go through basic MPLS concepts. A label switch router, LSR, is an MPLS-capable network device, such as a router and a switch. The device can forward packets based on the MPLS label header in the packets. A series of consecutive LSR'S constitutes an MPLS domain. A label edge router LER, is located at the edge of an MPLS domain and connects to devices on another network. For example, R1 and R3 in this figure function as LERs. A label-switched path is a path along which a labeled packet is transmitted to a destination through an MPLS network. An MPLS network uses a label distribution protocol to distribute and learn labels to establish a label forwarding path for traffic. An LSP can be created manually or established automatically using a label distribution protocol. Note that an LSP is unidirectional. The Ingress LSR is the start point of an LSP. A transit LSR is an intermediate point on an LSP. The Egress LSR is the end point of an LSP. Both the Ingress and Egress LSRs are LERs. The forwarding equivalence class, FEC, is a data classification method. It defines a data flow in which packets have the same processing method and treatment during forwarding. A device allocates the same label to the packets mapped to the same FEC. Traffic of one FEC is forwarded in the same mode and through the same path. The Ingress LSR determines the FEC to which packets belong. Let's go through MPLS Basics. An IGP, for example, or SPF, must be run on the entire network. The IGP implements connectivity between devices within the backbone network, not between the backbone network and another network. The IGP is used to maintain the routing table and FIB table. After learning routes, a device runs a label distribution protocol. In this example, a dynamic LSP is established. After a routing protocol is run, the device creates a routing table. Then, the device runs LDP, which is a dynamic label distribution protocol. LDP automatically distributes labels based on route prefixes. In this way, an LSP that traverses the entire MPLS domain is established using LDP. Then the device maintains related entries. These entries are called label FIB entries, containing the incoming and outgoing label values. Note that the outgoing label sent by each device is assigned by the next hop. After receiving an IP packet, R1 searches the FIB table and finds that the packet destined for 3.3.3.0/24 is forwarded to R2. R1 then pushes label 1033 into the packet and forwards the packet to R2. After receiving this packet, R2 obtains label 1026 from the packet, searches for this label in the LFIB table, and finds that the packet needs to be forwarded to R3. R2 then swaps incoming label 1026 for label 1092 and forwards the packet to R3. After receiving this labeled packet, R3 searches the LFIB table for an entry mapped to incoming label 1092 and finds that the mapped action is POP. Then R3 removes the label and forwards the original IP packet out of the LSP. The MPLS structure consists of the control plane and data plane. The control plane generates and maintains routing information and label information. On the control plane, LDP generates label mapping for route prefixes and distributes labels. The route prefixes are originated from the dynamic routing protocol, including IGP route and label information. On the control plane, two protocols are involved, that is, LDP and IGP. The data plane forwards IP packets and MPLS labeled packets. The data plane involves the FIB and LFIB. When receiving regular IP packets, the data plane forwards the packets based on the IP FIB or LFIP as needed. When receiving labeled packets, the data plane forwards the packets based on the LFIP. If the destination resides on an IP network, the data plane removes these labels and forwards the packets based on the IP FIP. On the control plane, a dynamic routing protocol generates routing information and saves the routing information to the RIP table. LDP distributes labels, creates the LFIP, and establishes or tears down LSPs. For more information, we will talk about later. This is the MPLS structure. The upper part is the control plane, and the lower part is the forwarding plane. On the control plane, devices run a dynamic routing protocol to exchange packets, generate backbone network RIS, and install RIS into the RIP table. In addition, the devices run a label distribution protocol to distribute labels. LDP is one of the mainstream label distribution protocols. The routing information installed into the RIP is automatically downloaded into the FIP to guide the forwarding of IP packets. In addition, the routing information in the RIP is used in LDP label distribution. When receiving an IP packet, a device forwards the packets in either of the two modes. 1. The device searches the IP FIP table for a matching route and forwards the packet over the route. 2. The device searches the LFIP table for a matching label, adds the label to the packet, and forwards the packet based on the label. When receiving a labeled packet, a device searches for an outgoing label or action mapped to the incoming label carried in the packet. If the action is POP, the device removes this label and restores the original IP packet before forwarding the packet. If the action is swap, the device swaps the existing label for another label before forwarding the packet. Next, let's look at the MPLS label structure. First, the label header is placed between the layer 2 frame header and the IP header. The label header can be considered as at layer 2.5. A complete label header contains 4 fields. The label field is 20 bits long and used to store a label value. The EXP field is usually used as a cause field. If traffic congestion occurs, the packets with a higher priority are transmitted preferentially. The both field indicates whether a label is at the bottom of the label stack. The TDL field is used to prevent labeled packets from being forwarded unlimitedly. One or more MPLS labels can be added into an IP packet. In this example, the IP packet has 3 labels added. Each label header is in the format shown in this figure and contains the both field to indicate whether the label is at the bottom of the label stack. If a label is at the bottom of the label stack, the IP header follows the label. In this case, the both value is 1. Otherwise, the both value is 0. The type field in the layer 2 frame header indicates the type of packet following the frame header. If its value is 0x0800, an IP packet is encapsulated with the frame header. If the value is 8847, which indicates unicast, or 8848, which indicates multicast, an MPLS label packet is encapsulated with the frame header. As we know, the label length of 20 bits indicates a large label space. Labels 0 to 15 have special meanings. For example, label 3 is an implicit null label. Its meaning will be described later. Labels 16 to 1023 are primarily shared by static LSPs and static CRSPs. Labels 1024 and greater are used by dynamic signaling protocols such as LSP, RSVPTE, and MPBGP. For a device, the actions of processing MPLS labels include push, swap, and pop. When an IP packet enters an MPLS domain, the MPLS LER adds a new label between the layer 2 header and the IP header of the packet. A transit LSR replaces the label on top of the label stack in an MPLS packet with another label, which is assigned by the next hop. When the packet leaves the MPLS domain, the label of the MPLS packet is removed. Here is a typical example. After an IP packet is received, the Ingress pushes label 300 into it. For an IP packet with a label stack, the device pushes label 300 into it. Label 200 is replaced by label 300 on the top of the label stack. Note that the label swap operation is generally performed on a label at the top of the label stack, so as the pop operation. Next, let's talk about LSP establishment. MPLS needs to allocate labels to packets in advance and establish an LSP before forwarding packets. LSPs can be either static or dynamic. A static LSP is established by manually allocating labels to each FEC. Nodes on a static LSP, however, cannot detect the status of the entire LSP. In addition, the LSP established by statically allocating labels cannot be dynamically adjusted based on network topology changes. Therefore, other methods must be used to discover a static LSP. Static LSPs are applicable to small networks with simple and stable topologies. Dynamic LSPs are used in common cases. They are established using LDB, RSVPTE, and MPBGP. When configuring a static LSP, follow the rule that the outgoing label value of an upstream LSR is equal to the incoming label value of a downstream LSR. A static LSP is established without label distribution protocols or the exchange of control packets. The static LSP has a low cost and is recommended for small-scale networks with simple and stable topologies. NHLFEs are used to guide the forwarding of MPLS packets. The content of an NHLFE includes the tunnel ID, outbound interface, next hop, outgoing label, and action for labels. You can obtain detailed FTN information in the entries whose tunnel IDs are not 0x0 in the fib. The FTN entries exist only on the Ingress LSR. ILM information includes the tunnel ID, incoming label, inbound interface, and action for the label. A transit LSR uses ILM entries to bind labels to NHLFEs. Querying the ILM table by label is equivalent to querying the fib by destination IP address. You can obtain all label forwarding information in the ILM table. Some upper layer applications, such as VPN and route management, may use tunnels. To provide a unified interface for such applications, the system automatically allocates an ID to each tunnel. Such an ID is also known as a tunnel ID, which is 32 bits long and valid only on a local node. The tunnel ID is allocated to each tunnel. In MPLS, tunnel IDs are also used to associate the fib, ILM and NHLFE entries. The Ingress LSR searches the FIB and NHLFE tables for matching entries used to forward packets. When an IP packet enters an MPLS domain, the Ingress LSR searches the FIB and checks whether the tunnel ID mapped to the destination IP address is 0x0. If the tunnel ID is 0x0, the Ingress LSR performs regular IP forwarding. If the tunnel ID is not 0x0, the Egress LSR performs MPLS forwarding. In this example, after receiving a data packet destined for 4.4.4.4, the Egress LSR searches the FIB for tunnel ID mapped to the destination IP address, finds an NHLFE mapped to the tunnel ID in the FIB, checks the NHLFE information for the outbound interface, next hop, outgoing label, and action, which is push, and pushes the label into the IP packet. Each transit LSR searches the ILM and NHLFE tables for matching entries used to forward MPLS packets. In this example, R2 and R3 search the ILM table for a tunnel ID mapped to the MPLS label, find an NHLFE mapped to the tunnel ID in the ILM table, and check the NHLFE information for the outbound interface, next hop, outgoing label, and action for the label. If the Egress LSR receives an IP packet, it searches the routing table and forwards the packet over an IP route. If the Egress LSR receives an MPLS packet, it searches the ILM table for an action for the label. If the S field in the label is 1, the label is at the stack bottom, and the packet is forwarded over an IP route. If the S field in the label is 0, there is a next layer label, and the packet is forwarded based on the next layer label. That's all for the MPLS overview. Thanks for watching. For more video clips about MPLS, stay tuned.